welcome. I'd like to cover or spend some time covering today a topic. We talked about the nucleus as we talked about the structure of the atom. We talked about what's inside of the nucleus. We learned that the nucleus was made up of protons and neutrons. We learned that the atom had an electron cloud. But specifically in looking at the nucleus, I wanted to just spend a minute, a day if you will, kind of discussing some basics about the nucleus, just so you kind of have an idea of why it's so important that we understand that the nucleus doesn't change. Now, we won't spend a lot of time on this. Like I said, we're just going to spend one day. There's a little bit that you'll be tested over when you take your exam on atomic structure, and then we'll just kind of move on from there. But, you think about the nucleus of an atom, and what you don't realize is that the nucleus of an atom is actually why we have a lot of the different energy sources we do, whether it's talking about something like the sun that gives us the energy that our planet needs just to survive, or whether it's something like a man-made like atomic bomb that simply takes the energy from an atom and uses that energy to produce such a large amount of heat and explosion. Another example is even the use of the nucleus of an atom to actually produce usable energy. We actually can use nuclear reactions to make an energy that can do things like run power grids. And so in talking about nuclear reactions, that's really what we're looking at. We're looking at the energy inside the nucleus and what happens as this nucleus starts to break down. So again, we're going to just talk a little bit about some basics about this, and then we'll come back to it when we look at chemical reactions later on in the year. But let's just talk. You were asked to do some research on atoms, specifically on different kinds of particles that we're going to find in the nucleus. They're called beta, alpha particles, and positrons. And then you were asked to fill in some information, including mass, charge, location, and symbol. Now, in order to do that, the first thing I want you to understand, in terms of understanding, we talk about the nucleus being protons and electrons. And remember, we said that protons are positively charged. Neutrons, which are also in the nucleus, we've always said that they were neutral. And then electrons that are in the electron cloud, we've always called them negative, right? But what we don't understand, and what we oftentimes don't see, because we just think of the proton as one particle, is that the proton is actually many different smaller particles all mixed together, and these particles giving off a positive charge. Same idea with the neutrons, made up of many different smaller particles that give off a neutral charge, no charge. And so as we think about what's inside of them, these particles, these smaller particles that we're talking about, are things like alpha particles, or even positrons, or even beta particles. There's others called neutrinos, as well as others called leptons, which we could keep going, and gluons and muons and so on. But we're going to kind of just leave it as the basics for right now. If you were to go into something like chemistry class in college or an AP chemistry class, you might learn more about some of these other particles. But we're going to focus just on these three. With that being said, the question is, for an alpha particle, beta particle, positron, what is the mass, charge, location, and symbol? So let's just start with mass. An alpha particle's mass is a mass of 4 AMUs. Now, the reason why is because an alpha particle is really just a helium nucleus. So it's got a mass of 4. Now you think about why. It's because when you lose an alpha particle, you're losing 2 neutrons, 2 protons, you're losing a helium nucleus. And that's what a helium nucleus is. It's just simply 2 neutrons, 2 protons within a nucleus. Now, what is the charge of an alpha particle? Well, an alpha particle simply has a charge of +2 because you're losing... Well, just that, right? You're losing a helium nucleus. So you're losing 2 protons that are positive, 2 neutrons that are neutral. So it's overall going to have a +2 charge. Location. The location of the alpha particle is it comes out of the nucleus. Symbol. the symbol of the alpha particle would look like this. Simply put, what you can notice, like I said, you've got 4 mass, you've got 2 from the protons, and you've got helium, which is what an alpha particle is. Alright, beta particle. A beta particle is really just similar to an electron. It's a negatively charged particle. Alright, it has no mass. Think about electrons. Electrons generally don't have mass, right? Well, a beta particle has no mass. Its charge is -1, and same idea, it's coming out of the nucleus. Now the question is, where is it coming from? Well, it's actually coming out of a neutron. The reason that neutrons are neutral is because they're made up of particles that are positive and particles that are negative in equal amounts. If you lose one of those negatives, then no longer would it be considered a neutron. So it's coming out of a neutron. The symbol for a beta particle is going to look something like this. It's going to say 0 for mass, -1 because you're losing 1, and either an E, or you might see it with a B for beta. Either way is fine, and that simply represents a beta particle. Alright, positron. A positron is just how it sounds. It's a positive particle. It's like a positive beta particle, if you will. So it's a positive particle. It has no mass. It has a charge of +1. Again, it's coming out of the nucleus. Specifically, it's coming from a proton. Now think about it. If a proton is positive and it loses a positive particle, that's going to cause a proton to become a neutron. So you picture what happens up here is a neutron will turn into a proton. Down here, a proton, by losing a positive charge, is going to turn into a neutron. A positron particle will look something like this. Or, again, same idea. You might see it written like that. But that's it. Alright, keep that in mind as we move forward. We're going to look a little bit at what radioactive particles are, what it means when we say radioactive decay. You'll have a little bit of practice problems that will go on with it and so on. Alright, so in order to understand why it is that the nucleus can lose particles and what's going to happen when it does, you need to understand some forces of nature. The 4 forces of nature, you think about forces, these are the only naturally occurring forces inside of the atom from strongest to weakest. So this is the strongest. This is the weakest. That's right. Gravity is actually the weakest force in nature. And you say, well, wait a minute. If I go to jump out of a window, I know that I'm going to fall to the ground. Well, that's because gravity pulls you to the ground, but it does not pull apart the particles inside of you, which is why you as a whole falls to the ground. It's not like some of your atoms fall and then other atoms and so on and so forth. Gravity is a very weak force. Now, the strongest forces are the forces in the nucleus. These 2 forces up here, the strong force and the weak force, these are both forces inside of the nucleus of an atom. Strong forces hold neutrons and protons in place. Weak forces hold neutrons together. Now what happens is as these forces start to split, as these forces are broken, if they are broken, they will give off a lot of energy, and we're going to see that in just a minute. Electromagnetic force is a force that maybe you've heard of before, maybe not, but just make a note. This is the force between protons and electrons. It's like talking about a magnet, right? You bring 2 sides of a magnet together, two different sides, you know they're going to attract. Two sides that are the same are going to repel. That's an electromagnetic force. It's the idea that opposites attract. All right, so again, it's the force between protons and electrons. All right, in order to understand what happens inside of the nucleus, we need to understand that what holds the nucleus together is the protons and the neutrons. The more equal they are, the more they're going to hold themselves together within the atom. As you increase the protons or as you increase the neutrons, it will change the stability of the atom itself. Now, to get that, give you an idea of that, this is what tells us how stable atoms are. Now, we call it the band of stability, and you can write out as much or a little of this as you want, but all these atoms inside of this bands, they are stable, and they're going to stay stable. Their nucleus is not going to break apart in order to become something else. What happens is as you go above, so if you want to picture, if this is the amount of protons, and these numbers are the amount of neutrons, the more equal they are, the more likely they are to be in this band of stability. And that's where you see all these little spots. These are the atoms that you find on the periodic table. Well, as they go above, so as you start to see protons and neutrons go above that band of stability, you can start to see them do various things. For example, they might release a beta particle. We had just said that that's really just a negatively charged particle. They might release an alpha particle. We had already said that really we're just talking about a helium nucleus. They could even capture something like a beta particle. So they could even bring in an electron from where? From another nucleus. Or even from the electron cloud. They could also emit a positron, right? Remember we said a positron is a positively charged particle. So just depending on where they are on this band of stability, the nucleus can actually start to break down. Now this word that we use to describe the breakdown of a nucleus, maybe highlight it or make a note of it, but it's called radioactivity. When we hear the word radioactivity, that simply means the breakdown of the nucleus of an atom. And when that happens, it means a release of energy. You might even have heard it in the past called radioactive decay. Alright, so with this in mind, these are some different types of radioactive decay. We've already talked a little bit about them, but we simply could be looking at alpha particles, beta particles, gamma particles, or positrons. Now remember we said an alpha particle is really just a helium nucleus. Again, if you want to write this down, again, you can. A beta particle is really just an electron. A gamma particle we haven't talked about, but it's because it's not a particle. It's just a high wave of energy. And then a positron, which is really just a positive particle. So what we're going to see as we look through these different types of radioactive decay is how these different particles are released. So let's just start with alpha particles. Now, you think about it, what's happening when an alpha particle is released? Well, remember, we said it's releasing a mass of 4, and it's releasing 2 protons, right? So it's 2 protons, 2 neutrons. Notice what happens when something like that happens. So let's just say we had element radium, Ra, with a mass of 226. Now we want to picture this would be like saying Ra with a mass of 226 and 88 protons. When it releases an alpha particle, here's what happens. It releases a mass of 4. So if we take 4 away from 226, we really just have 222. It releases 2 protons. we take 2 away from 88, we really just have 86. So by alpha particles being released, well, we took radium and we turned it into a new compound, or a new substance, called radon. That's what alpha particle emission looks like. Now, we're going to do a couple of them in just a minute, a couple of them on your homework, and then you're going to practice doing some on your own. Now, again, notice it's really just subtraction, right? So if you have a mass of 226 and you took 4 away, you end up with 222. If you had 88 protons and 2 of the mass you took away was protons, you went from 88 to 86. All right. Beta particle emission. Now remember, a beta particle is an electron, and that electron comes from the neutrons inside of the atom. You might be saying, what is an electron doing inside of a neutron? Well, remember that a neutron is neutral because it's made of positives and negatives in equal amounts. So what happens when an electron is emitted? Well, what happens is a neutron becomes a proton. It gives up one of its negative charges. It now is positively charged, and notice what happens. Notice that carbon-14 that had 6 protons, if it got rid of an electron from that neutron, remember we said a neutron becomes a proton, so now we have 7 protons, but the mass did not change, right? Because we said beta particles have no mass. So we turned carbon into nitrogen. Again, notice what happens. Really now we've got 6 as protons. Notice that we got rid of an electron because the neutron became a proton, and now notice we've got 7. Now, a way you can look at this is the math has to equal, right? So notice 14, notice 0 plus 14, notice it didn't change. Down here, notice we have 6, notice negative 1 and plus 7. Notice that it's still 6. Notice whatever we started with, we ended with. All right, so the math has to equal. So if you want to look at this as just a math problem, that's fine. But another way to look at it is, like we said, an electron was emitted from a neutron in the atom. All right, again, I'm going to go over a couple with you in just a minute before you do your homework, but let's just take a look at a couple more. So that's beta particles. Gamma particles are just energy. I'm not going to ask you to worry about those other than to just know that the atom doesn't change. It just gives off a lot of energy in gamma particle emission. All right, now again, you already have all this written down from your notes from yesterday, so I just wanted to make sure you kind of know what's going on. But let's talk about positron emission. Same idea, all right? So we've got potassium with a mass of 38. Potassium's atomic number is 19, and then it emits one of its protons. Now remember we said the proton is coming from where? That positive particle is coming from a proton. So now we're going to have one less proton. Remember, a positron particle's mass doesn't have one. And so here's what we get. We have potassium emitting one of its protons. Now remember, when it gets rid of that positive particle of its proton, it becomes a neutron, right? We just said that before. The positive particle causes that proton to become a neutron. A proton turns into a neutron. So notice what happens. Notice we have one less proton, but the mass is still the same. Notice again that everything equals, right? So 38, notice we got 38 plus 0. The mass didn't change. Notice that the positives didn't change, right? 18 and plus 1 is 19. Notice we have 19 over here. All right. Again, you can look at this as a math problem or look at it as the idea of what's happening inside the nucleus of the atom. All right, electron capture, same idea. So let's take a look at what's going on. All right, so we've got argon, which has a mass of 37, 18 protons, and then it brings in one of those negatively charged particles, we call them beta particles or electron captures. It brought in an electron. So what happens? Well, that electron and a proton inside of the nucleus, they're going to combine and form a neutron. So the mass didn't change, but now we've got one fewer electron. So we want to picture electron capture. A proton pulls in an electron, turning into a neutron. Think about why that is. If a proton is positive, electron is negative. If a negative is pulled into a positive, what happens? It becomes neutral. All right, so a proton pulls in an electron, turning into a neutron. Notice the same idea as what we just talked about before. The math has to equal. So 37 and 0 is 37 on both sides. We got 18 minus 1, which is 17. We got 17 over here. So in the end, the math has to all equal. All right. Again, we're going to go over a couple of these in just a minute. Just something to make a note of, these particles, depending on how strong they are, they can penetrate different things. And that's actually why it's important to understand that alpha particles can be extremely dangerous. They cannot penetrate our skin, but we can consume them. If we were to consume them, they could make us very sick. Beta particles actually can penetrate through a lot more. They can go all the way through our skin. They can go into something. Ultimately, they could be dangerous, but we really don't see them actually affecting us because they're not around us that much. Gamma particles can basically penetrate anything except for lead. They are, again, high energy particles. We are going to stop there in terms of notes. There is more to this PowerPoint in dealing with reaction series, as well as in dealing with actually the math that goes along with it. But we're going to hold off on that until I get back, just because that can be somewhat complex, and I would rather be there. That way, as we're going through it, we can answer lots of questions. All right, so let's hold off on that. Ms. Golson's going to go ahead and pass out to you your homework, and I'm going to take a minute, and I would like to look at a few of the problems from your homework with you. This is what your homework is going to look like. So please make sure that you get one of these sheets, and in just a minute, I will go over a few of these problems with you. All right, let's go ahead and take a look at a couple of the questions on your homework assignment just to get you set up for what you're going to be doing. So if you would have your homework sheet in front of you, again, Ms. Golson should have just passed it back. And it says nuclear decay on the heading. And you'll see the very first question should look something like the one you see on the overhead in front of you. It says the following atoms undergo alpha particle emission or alpha decay. So write the complete nuclear equation. Now I want you to remember that when something undergoes alpha decay, neutrons, which is why, remember, it's a mass of 4, right? So a mass of 4, an atomic number of 2. So right off the bat, in every single one of those problems, the one with polonium and uranium and thorium and radon, the very first thing we could put in each of those blanks is that a helium nucleus is being released. That doesn't change for every single one of those problems. Because it says it's alpha decay, you're giving off a helium nucleus. So now, what should the other substance be then? Well, remember that the numbers at the bottom and the top of these formulas, remember we called these shorthand formulas, the numbers have to equal. So if we're giving off a mass of 4, then that means that whatever we have left over, even before we figure out what it is, well, it's going to have 4 less mass, which means 206, right? We lost 2 protons, we lost 2 neutrons, so no longer do we have a mass of 210, we gave off 4 of it, so now we've got a mass of 206. Now, same idea with the protons, right? The atomic number, remember we started with 84, but it lost 2 of those, because like we said, we lost 2 protons. which means we've now gone down to a mass of 82. I'm sorry, an atomic number of 82. Now it's just a matter of looking on the periodic table and seeing what element is atomic number 82. And again, notice that the atomic number 82 is the element Pb. So in that first blank, we would have written 4, 2, and He. In that second blank, we would have written that we have 206 for mass, 82 for atomic number, and the symbol is Pb. All right, I'm going to do one more with you, and then you can do the other two on your own. So uranium, we see it says 238 for its mass. It says 92, because that's uranium's atomic number. And it tells us it's going through alpha decay, which again, right off the bat, like I just said, means that first blank should be a helium nucleus, right? Every single one of those 4 problems underneath that alpha decay section, that first blank is going to be a helium nucleus. So let's talk about mass. If we gave off a mass of 4, we now have a mass of 234. We gave off atomic number of 2. We now have an atomic number of 90. And again, we can find it on the periodic table, and we can see that element number 90 is what? It's thorium, Th. Alright, y'all, I did those 2 with you. I'm going to ask you to do the other 2 on your own. I'm going to do one of the others. So let's do 1 beta decay, 1 electron capture, and then 1 positron emission. And then I'm going to ask you to try the others on your own as well. And then, like I said, this will be your homework. Finish whatever you don't finish in class at home, and then we'll check, or you'll check your answers tomorrow in class. Alright, so let's do the next one. It says the following, so the next section underneath the alpha particle emission, the next section says the following atoms undergo beta decay. So write the complete equation form. Alright, so remember, beta decay means the release of an electron, right? It will look something like that. So no change in mass, -1 for what we would say electron. Now we've got a neutron. Remember, in beta decay, a neutron turns into a proton. So what does that mean? It means no mass change. Protons increase by 1. Alright, so let's look at a couple examples. Let's start with carbon-14. We see that first one says 14 for mass, 6, and C, right? That's carbon-14. It tells us it undergoes beta decay, which again means since every single one of those problems in that section undergo beta decay, for every single one of them, the very first blank should look the same, right? They're all giving off the same particle. So for carbon-14, the first blank is going to show that beta particle, that electron being given off from the nucleus. Now remember, when it's given off, remember that means that a neutron becomes a proton. Remember, protons increase by 1. No mass change, so 14 for the mass. Protons increase by 1, so 7 for the protons. And we look on the periodic table and we see atomic number 7 is nitrogen. And now we've got beta decay of carbon-14. Remember that the numbers have to add up on both sides, right? So this 14, notice we got 0 and 0, 14, which is 14. Notice we got 6, and then we've got -1 and +7, which is 6. So, again, beta decay for carbon-14. Let's do one more. So, next one, we see strontium, 90. Alright, it looks something like this. Again, same idea, because it's still under that beta decay section. The very first blank is going to look like that, right? It's undergoing beta decay. So what does that mean for everything else? Well, remember, no change in mass. So mass is still 90. Remember that a neutron turns into a proton, right? Proton goes up by 1. so it becomes 39. And then we look, we find it on the periodic table, and we see that element 39 is deuterium, which is Y. And we're done. Alright, let's go ahead and look at the next. So you can do the other two beta decay ones on your own. Do the best you can. Again, remember, the very first blank for those should be the same. What's going to be slightly different is that second blank. So let's go ahead and let's look at the next section, which is electron capture. Now remember, in electron capture, that electron is coming from outside of the nucleus. It could be coming from the electron cloud. So we've got an electron coming in, right? It's coming in to the atom, and that means what? It means a proton is going to turn into a neutron. So protons will decrease by 1. No change in mass. Alright, so let's just start with the first one. The first one says silver 106, so we see 100 and for the mass. Silver's atomic number is 47. Notice now that the blank is on the other side of the reaction, right? Because it's now a reactant. It says electron capture. It's coming in to the nucleus. So now that blank for every single one of those is going to be the same, because for every single one of those it's capturing an electron. So an electron is coming in. So remember, no change in mass. So the mass is going to stay the same. But remember, we said protons decrease by 1, right? So minus 1, so this is going to become 46. Find it on the periodic table, and we see that element 46 is palladium, or Pd, and we're done. That would be electron capture. Alright, let's do the next one as well, so that we just make sure we've got what we're doing. We see it is 10-116. So 10-116, atomic number is 50. That's what it looks like. Now remember, again, since this is electron capture, that blank on the reactant side is going to stay the same. It's an electron coming in, so every single one of those, all 4 of those problems under electron capture, they're all going to look the same. So remember what is happening. No change in mass. The mass stayed the same. Remember, protons decreased by 1. So that 50 became 49. We look, we find 49 on the periodic table, and we see that 49 is indium. And that's it. We're done. Alright, y'all, I'm going to do the last one, or the last section for you, the positron emission section. So if you'd flip to this back side, or the second page for me, and then after that, you have the remainder of the period to... Alright, I'm going to do the last section, the positron emission section, then you can have the remainder of the period to work on any of these problems you didn't get... I'm going to give you the remainder of the period to work on the problems you didn't get finished really quickly. I'd like to go through that last section with you. That last section that says positron emission. And just make sure you're able to do that, and then that will be it. And like I said, I'll give you the remainder of the period to work on the rest of the problems. Otherwise, it will be your homework for tomorrow. So positron emission. Now remember, in positron emission, it means that a positive particle is being released, right? So a positive particle is being released. Now remember what that means when that happens. That means that a proton turns into a neutron. Alright, now With that in mind, that means that the number of protons will decrease by 1. No change in mass. Alright, so let's just take a look at the first one. Again, we've got 10 1/16, so 1/16, 50 on the bottom. Alright, so just like the other ones, just like the ones we looked at previously, that first blank is going to stay the same, because if we're emitting a positron in all of them, that first blank should all look like we're emitting a positron, which would look like that. Now remember, we said no change in mass, so that second blank is going to stay 1/16. Remember, we said that the protons decreased by 1, right? So that 50 is going to become 49. Remember that all the numbers have to stay the same on both sides. We got 1/16. We got 1/16 for the mass over here. We got 50 protons. We've got plus 1 and 49. We got 50 total over here. Now it's just a matter of plugging in. And we see that through positron emission, much like through the one we looked at on the previous, which was electron capture, through positron emission will produce indium again. Alright, so that would be the first one. Alright, let's look at the second one real quick. It says copper 61, so we've got a mass of 6. It says copper 61, so we've got a mass . We've got a mass of 61. We've got copper, which is atomic number 29. Remember, as we had said for the previous, because it is positron emission, that first blank is going to be a positron. Every single first blank in that section, so all 4 of those problems, they'll all be a positron that's emitted. What does that mean for the second blank? Well, remember, no change in mass, so still a mass of 61. Remember, 1 less proton. So instead of 29, we now have 28. Look and find element 28 on the periodic table, and we see that it is nickel, and we're done. That's it. That's positron emission of copper 61. Alright, y'all, I've done 2 of each of them in each section, which means you have the other 2 for each section to do, along with the last section that asks you to see if you can figure out what each of them are, and then fill in the blanks. Go ahead and spend the remainder of the period doing that now. Otherwise, this will be your homework for tomorrow. One more thing really quickly. There is more to this PowerPoint. However, we're not going to spend more time this week talking about the remainder of this PowerPoint. You will not be responsible for the remainder of this PowerPoint in terms of the quiz or test coming up. We will come back to this information later on in the year. This section right here, simply looking at these types of ways that the nucleus can break down, is where we will stop in terms of understanding radioactive decay. And then, as I said, we will come back and we will touch on it at a later date. If you should have any questions, please don't hesitate to ask. Otherwise, let me remind you, you will be taking a test quiz, if you will, on the material you've been talking about with atomic structure, as well as this information on Thursday of this week. That's it. I hope you have a great day.